Welcome to Wings of Arrow Advanced Education and Research Organization. To know more, visit our official webpage www.wingsofarrow.in. Find your dream aviation and aerospace jobs at www.wingsofarrow.in/jobs. Consider an electric propulsion thruster. Determine the flight characteristics of an electric propulsion thruster for raising a low satellite orbit. The following typical values are given. Specific impulse is equal to 2000 seconds, thrust is 0.20 N, propulsive time 4 weeks, and payload mass is equal to 100 kg. Specific power of the power plant is 100 watt per kilogram and thruster efficiency is equal to 0.5. Consider an electric propulsion thruster. Determine the flight characteristics of an electric propulsion thruster for raising a low satellite orbit. The following typical values are given. Specific impulse is equal to 2000 seconds, thrust is 0.20 N, propulsive time 4 weeks, and payload mass is equal to 100 kg. Specific power of the power plant is 100 watt per kilogram and thruster efficiency is equal to 0.5. Given data. Here the specific impulse I suffix s is 2000 seconds. Specific impulse at a speed which is effective exhaust velocity. Thrust F is equal to 0.20 Newton. Propulsive time T suffix P is equal to 4 weeks or 2.42 into 10 to the power 6 seconds. Payload mass M is equal to 100 kg. Specific power of the power plant alpha is equal to 100 watt per kilogram. Thruster efficiency eta suffix T is equal to 0.5. Now we have to find out the flight characteristics for raising a low satellite orbit. In electric propulsion, the term thruster is used the same way as engine is in liquid propellant and motor in solid propellant rockets. First, find propellant mass flow. For constant thrust and negligible start or stop transients, propellant flow can be written as m dot is equal to F divided by I suffix s into G naught. Here F is the thrust, I suffix s is the specific impulse, and G naught is the standard acceleration of gravity with an average value at the Earth's sea level of 9.81 meter per second square. Now substitute the given known values and simplify. We get the required propellant mass flow is 1.02 into 10 to the power minus 5 kilogram per second. Next, find the total required propellant. For a cumulative period of operation, the amount of required propellant is the product of mass flow rate and time period. Then write m suffix p is equal to m dot into t suffix p, where Tp is the given duration and m dot is the propellant mass flow which we have found out. Solve this equation with known values. Thus the total required propellant is 24.69 kg. Next, find the required electrical power. We know that thruster efficiency is defined as the ratio of thrust producing kinetic power of the exhaust beam to the total electrical power applied to the thruster. From this we can write for the required electrical power. P suffix E is equal to 1 divided by 2 into m dot into V square divided by eta suffix T, where m dot is the propellant flow rate, V is the effective exhaust velocity which is given in the question as specific impulse, and eta suffix T is the thruster efficiency. Substitute those values and solve Thus we have the required electrical power is 3.92 kilowatts. Next, find the mass of the power plant. Specific power is considered to be proportional to thruster power and reasonably independent of total useful propellant mass. Its value depends strongly on the type of electric thruster and somewhat on the engine module configuration design. Then we can write the mass of power plant m suffix pp is equal to p suffix e divided by alpha, where p suffix E is the electrical power and alpha is the specific power. Now divide electric power with the specific power. We get the required mass of the power plant is 39.2 kilogram. Next, find the velocity increase. The velocity increase of the vehicle under idle vacuum and zero gravity conditions, delta U is equal to V into ln of m naught divided by m naught minus m suffix p, where m naught is the initial mass and m suffix p is the propellant mass. Initially, payload mass and propellant mass m suffix p and the power plant mass m suffix pp are there. Then initial mass m naught is equal to 163.9 kilogram. Now substitute the appropriate known values, then solve. We have the required velocity increase, delta U is 3200 meter per second. Next, find the acceleration of the vehicle. The acceleration of the vehicle is the ratio of velocity increase to propulsive time. Then A is equal to delta U divided by T. Substitute known values and simplify. We get the required acceleration is 1.35 into 10 to the power minus 4 g naught. The flight's energy increase after 4 weeks of continuous thrust producing operation is not enough to get from low Earth orbit to geostationary equatorial orbit, which would have required a change of vehicle velocity of about 4700 meter per second with continuous low thrust as compared to the 3200 meter per second above. During its travel, the satellite would have made about 158 revolutions around the Earth and raised the orbit by about 13,000 kilometers. Moreover, this case does not represent an optimum. Did you know? Its founder is an internet mogul. The guy who wants to take you into orbit was one of a handful of guys who made it easier to pay for stuff online. Elon Musk, 40, a South African by birth, was a co-founder of PayPal. After cashing out on that venture, Musk got into futuristic transportation, sinking funds into electric cars and SpaceX. It beat the competition into orbit. SpaceX shot ahead of the competition in 2010 when it became the first private venture to launch a craft that circled the globe, sending up a Dragon capsule that went twice around the world before parachuting back into the cool waters of the Pacific Ocean. The There and Back Again mission was a crucial stepping stone for the company on its path to sending a manned craft into the ether.
If you have further inquiry or requested video, drop down to our mail wingsofarrow@gmail.com. Don't forget to subscribe for more updates. For the time being, take care, stay blessed, inspired and fly high.